Hey guys, Mr. Mises here, and in this video I'd like to talk to you about the limit comparison test. The limit comparison test, is just like the comparison test, only we have to take a limit. So it's useful when we're dealing with messy algebraic series, but we want to compare it to an easier p-series. So think of a rational series. So we have polynomials on both the numerator and the denominator, or maybe square roots in the numerator and the denominator, or some sort of roots that we can compare to an easier p-series, but it can't do the direct comparison test because it doesn't, you can't just say, oh, one's less than the other one, right? Or one's greater than the other one, and it's really easy to see. It's a little bit for more messier situations, but the work itself is not very messy. So what we're going to do is when we do choose our p-series, we're going to disregard all the stuff in a series except for the highest powers of n in the numerator and the highest powers of n in the denominator. So we're going to take those and we're going to basically simplify that, and that's going to be what we're going to compare it to, if that makes sense. So let's take a look at some examples. Here is a limit comparison test on what we're looking to try to accomplish. And what we're trying to accomplish is we're trying to find the limit as n approaches infinity of the ratio of a sub n and b sub n. And b sub n is going to be the one that we compare it to, and a sub n is going to be the one that we have. And we're going to divide those, and we're going to hopefully get a value. If the value there in the limit is positive and finite, then they're both going to converge. So, or they're both going to diverge, depending on which one the one we're comparing it to does. I think it's going to make a bit more sense when I do an example. Let's do an example. So I have 1 over 3n squared minus 4. So I'm going to take the highest power of n up here, which is just 1. And I'm going to take the highest power of n here, and that's n squared. And that's what we're going to compare to. All right, so this is going to be our b sub n. Now, what do we know about this one? Well, we know that this right here is a p-series where p is equal to 2, which is greater than 1. So it's going to converge, right? By the p-series test. So what we're going to do is we're going to use the limit comparison test. We're going to take the limit as n approaches infinity of a sub n, okay, 1 over 3n squared minus 4 over b sub n, 1 over n squared. I'm going to rewrite that. Limit as n approaches infinity, 1 over 3n squared minus 4 times n squared over 1. And then I'm going to find the limit. All right, well, the limit here is n squared over 3n squared minus 4, and the limit as n approaches infinity. This is just a horizontal asymptote. Those are even, so that's going to be 1/3. So 1/3, right, this is finite and positive. It equals to L, which is great. So using my limit comparison test, the series 1 over 3n squared minus 4, this series converges by the limit comparison test. Now it converges because this converged, all right? And we use the limit comparison test to do that. Let's take a look at number 5. All right, so what I'm going to do is take the highest power on the top, which is n to the 1/2, highest power on the bottom, which is n, and I'm going to simplify this, and that's going to give me 1 over n to the 1/2. And this is what I'm going to compare. Okay, so we're going to say we're going to compare to this series. This series diverges. How do I know it diverges? It diverges by the p-series test, because p is equal to 1/2, which is less than 1. All right, so now I'm going to use my limit comparison test. So the limit as n approaches infinity of a sub n, which is my original series, divided by divided by b sub n, which is the one I'm comparing it to. All right, so I'm going to rewrite that. Limit as n approaches infinity of n to the 1/2 times n to the 1/2 over n minus 7. And that's going to be the limit as n approaches infinity of n over n minus 7, right? N times 1, which is going to be 1. So this is finite and positive, finite and positive. So my series, square root n over n minus 1, diverges by the limit comparison test. Why did it diverge? Because the one I was comparing it to also diverged, okay? So hopefully that makes a little bit of sense. It's really not that hard. You just got to make sure that you are using, you're checking for this limit here. Let's take a look at one more. So we're going to take the highest power on top, which is n, the highest power on bottom, which is n cubed. We're going to simplify that to 1 over n squared. So we're going to compare to the series 1 over n squared, which we know converges. How do we know it converges? It converges by the p-series test, because p is equal to 2, which is greater than 1. All right, so we're going to do our limit as n approaches infinity of a sub n, which is n over 4n cubed plus n squared plus 5. And I'm just going to go and do the reciprocal right away. I think you guys figured out that that's what we're going to have to do, right? Okay, so this is going to be the limit as n approaches infinity of n cubed over 4n cubed plus n squared plus 5, which is 1/4, right? They match up, so we get 1/4, which is finite and positive. So the series n over 4n cubed plus n squared plus 5 converges, because the one we compared it to converges by the limit comparison test. All right, guys, there you go. That's the limit comparison test, and we'll talk to you soon.